we now discuss the solution of a problem from the section Algebra. The problem is on Euler's phifunction, and this question has appeared in CSIR National Eligibility Test held on 30th November 2020, and it is from the section C. The problem is, for a positive integer n, let phi of n be the Euler's phifunction. Which of the following statements are true for n greater than 3? We are given 4 options. Option 1, phi of n can never divide n. Option 2, phi of n divides n implies there exist integers x comma y such that nx plus 6y is equal to 1. Option 3, phi of n divides n implies n can have at most 2 distinct prime divisors. Option 4, phi of n divides phi of nk for every positive integer k. So, for any given positive integer n, phi of n denotes the Euler's phifunction, and we have to decide which of the following 4 options is true or are true for n greater than 3. It may be more than 1 also, because it is from the section C. So, let's get into the problem. Before that, we have a prelude on Euler's phifunction. The Euler's totient function or phifunction is defined as follows. The Euler's totient function or Euler's phifunction is a very important number theoretic function in number theory. The totient phi of n of a positive integer n greater than 1 is defined to be the number of positive integers less than n that are co-prime to n, that are relatively prime to n. For n belongs to n set of natural numbers, n greater than 1, phi of n is the cardinality of the set consisting of m belongs to n, where m less than n, and the GCD of m comma n is 1. That is, m and n are co-prime, or m and n are relatively prime. So, that means phi of n denotes the number of positive integers less than n that are relatively prime to n. So, phi of 1 is defined to be 1. Agreed. We now see some of the properties of the Euler's phifunction. First result, n is prime if and only if phi of n is equal to n minus 1. Result 2, if m and n are co-prime or relatively prime, if their GCD is 1, then phi of the product m n is equal to the product phi of m into phi of n. Result 3, if the prime factorization of n is given by n is equal to p1 to the power of k1 into p2 to the power of k2, etc., pn to the power of kn, where p1, p2, pn are distinct prime numbers, then phi of n is equal to n, the given prime factorization, you have to write, multiplied by 1 minus 1 by P1 multiplied by 1 minus 1 by P2, etc., etc., multiplied by 1 minus 1 by Pn. This is equivalent to the following. Phi of n is equal to P1 to the power of K1 minus 1, K1 minus 1 into P2 to the power of K2 minus 1, etc., Pn to the power of Kn minus 1 into P1 minus 1 into P2 minus 1 into Pn minus 1. These two are equivalent. Result 4. If Mn are natural numbers and if m divides n, then phi of n divides phi of n. If m divides n, then phi of m divides phi of n. Now let's get into the given problem and discuss its solution. We have a n, a natural number. Phi of n is its Euler's phi function and n greater than 3. This is the common hypothesis for all the arguments. Let's take the statement that is given in option 1. It says phi of n can never divide n. Either you have to prove in general, and if it is not true, then we give a counter example. We go for a counter example. Let n is equal to 4. Then phi of n is equal to phi of 4. 4 is 2 square. 2 square into 1 minus 1 by 2, and that is 2. Therefore, phi of n is equal to phi of 4 is equal to 2 divides n is equal to 4. So, phi of n can never divide n is not true. Here is an example. Phi of n divides n for n is equal to 4. Thus, for this n is equal to 4, phi of n divides n. Therefore, the option 1 is not true. Let's get into the next one. That's the common hypothesis. Let us take the statement that is given in option 2. Phi of n divides n implies there exists integers x comma y such that nx plus 6y is equal to 1. We take the same example what we have taken in option 1. We have for n is equal to 4, phi of n divides n. So assume that the statement given in option 2 is true. This implies there exists integers xy such that nx plus 6y is equal to 1. We recall a result from number theory. Let a and b be non-zero integers and c is any integer. Then the equation ax plus by is equal to c has integer solution for xy if and only if the GCD of a and b divides c. So by this result, there exists integers xy such that nx plus 6y is equal to 1. Using this implies that the GCD of n comma 6 must divide 1. The GCD of n comma 6 divides 1 means what? GCD of n comma 6 is 1. That is, the GCD of 4 comma 6 is 1, which is a contradiction. Why? Because the GCD of 4 comma 6 is 2. This contradiction tells you that your assumption is wrong. Therefore, the option 2 is not true. Let's get into the next one. There is a common hypothesis. Take the option 4. Phi of n divides phi of nk for every positive integer k. So this is true. So now recall, let m, n are coming from the natural numbers. If m divides n, then phi of m divides phi of n. This is a property of the Euler's phi function. So now n divides nk for every positive integer k, yes. Therefore, by using the above result, phi of n divides phi of nk for every positive integer k. So we use the above and this is true. Thus, the option 4 is true. Agreed. Now, let's get into the last one. That is the statement that is given in option 3. Phi of n divides n implies n can have at most two distinct prime divisors. Phi of n divides n implies n can have at most two distinct prime divisors. And this is true. We are going to prove it. Let the prime factorization of n be n is equal to p1 to the power of a1 into p2 to the power of a2, etc. pk to the power of ak, where p1, p2, pk are distinct prime numbers. Then phi of n is equal to p1 minus 1 into p1 to the power of a1 minus 1 into p2 minus 1 into p2 to the power of a2 minus 1, etc. pn minus 1 into, it's not 11, it is 1, pn minus 1 into pk to the power of ak minus 1. Note that now p1, p2, pn are prime numbers, and p1 minus 1, p2 minus 1, pn minus 1 are all even. And now, why n greater than 3? Why we are considering n greater than 3? N greater than 3, therefore, phi of n is even. Phi of n divides n, it is given to us, and phi of n is even, will imply n is even. When n is even, we have two cases to deal with. The first case is n is equal to a power of 2. And the case 2 is not only the power of 2, it is not only even, it's not only the power of 2, but there are some prime factors which are odd prime factors are there. So n is equal to 2 power a1 into p2 to the power of a2, p3 to the power of a3, pk to the power of ak, where p2, p3, pk are odd primes. So these are the two possibilities. So even means this is even, this is also even. And these are the two possibilities. In the first case, we have n can have at most two distinct prime divisors is true, because there is only one prime divisor 2. And case 2 we have to deal with, and we have to see whether this statement is true or not. Let's continue. Case 2, we have n is equal to 2 power a1 into p2 to the power of a2, p3 to the power of a3, etc. pk to the power of ak, where p2, p3, pk are odd primes. And let's take its Euler's phi function. Phi of n is equal to 2 minus 1, 1 into 2 to the power of a1 minus 1, p2 minus 1 into p2 to the power of a2 minus 1, p3 minus 1 into, this is p3, p3 to the power of a3 minus 1, this is p3, etc. pk minus 1 into pk to the power of ak minus 1. Agreed. Now, we claim that n has only one odd prime factor. In this, there is only one prime factor. In this, there is only one. How do we prove? Assume that n has more than one odd prime factor. Assume that n has more than one odd prime factor. Then, how many are these? How many are these? P2, P3, Pk. They are k minus 1. And they are more than 1, means k minus 1 greater than 1. Since P2 minus 1, P3 minus 1, Pk minus 1 are all even, then what will be the power of 2 in phi of n? The exponent of 2 in phi of n will be not only a1 minus 1, a contribution 2 will come. And how many contributions will come? K minus 1. So the exponent of 2 in phi of n is a1 minus 1 plus k minus 1. And that will be greater than a1 because k minus 1 is greater than 1. So that means the exponent of 2 in phi of n is greater than a1. Then how can phi of n divides n? Therefore, phi of n does not divide n. A contradiction. And our claim is true. What is our claim? N has only one odd prime factor. Thus, n has only one odd prime factor, say P2. So, n will be equal to 2 to the power of a1 into P2 to the power of a2 in this case. So, combining case 1 and case 2, n has at most two distinct prime divisors. What are they? 2 and P2. What is P2 is the question that I will discuss after this. So, n has, from case 1, n has only one prime divisor, namely 2. And from case 2, it has two prime divisors, 2 and P2. And P2 is an odd prime. So, thus, n has at most two distinct prime divisors. Thus, the option 3 is true. So, how many options are true? Our answer is the options 3 and 4 are true. This completes the discussion of the solution of the given problem. However, I will now prove in this case, in the case 2, P2 is an odd prime that I will show you P2 is equal to 3. And this is to be discussed, and it is important to note down. Let's discuss that in the next slide. Case 2 is continued. We have n is equal to 2 power a1 into P2 to the power of a2 for some prime P2 greater than 2, say R prime. Phi of n is 2 to the power of a1 minus 1 into P2 minus 1 into P2 to the power of a2 minus 1. Agreed. Our claim is P2 is 3 only. Now phi of n divides n, yes. Means what? N by phi of n is an integer, yes. N is 2 power a1 into P2 to the power of a2. Phi of n is 2 power a1 minus 1 into P2 minus 1 into P2 to the power of a2 minus 1. Cancelling the common factors, we will get 2 into P2 by P2 minus 1, and this is an integer. This implies P2 minus 1 must be equal to 2. Why? Because the GCD of P2 and P2 minus 1 is 1. P2 is an odd prime. P2 minus 1 is even. So, therefore, the GCD of that is 1. When the GCD of that 1 is, P2 minus 1 must divide 2. P2 minus 1 divides 2 means what? P2 minus 1 is 2. That implies P2 is equal to 3. So, in this case, P2 is 3. Therefore, n is equal to 2 to the power of a1 into 3 to the power of a2 in case 2. So, thus we have proved this very important result. If n is equal to 2 to the power of a1 into P2 to the power of P2 to the power of a2 for some prime P2 greater than 2 and phi of n divides n, this is a condition, it's a must condition, then n is equal to 2 to the power of a1 into 3 to the power of a2. N is equal to 2 to the power of a1 into 3 to the power of a2. Thus, our claim is fulfilled, and that's what I wanted to tell you about this case too. This completes the discussion of the solution of the problem on Euler's phi function. And it is definitely a very interesting problem, and I hope that you have understood the solution of this problem, and go on working out some more problems on these lines from number theory in algebra. I wish you all the best. Thank you.